Here's an animation environment that's worth looking at for understanding the concept of adiabatic cooling and adiabatic heating. It also may be something that we'll play around with later on in the term. But for right now, we've got a bunch of little molecules bouncing around in this container, and they're at a temperature of 284 Kelvin. So remember that the freezing point of water is either 0 degrees Celsius or 273 Kelvin, and so this is about 11 degrees Celsius. I can warm these molecules up by adding heat energy, putting a little fire underneath the thing, or I can cool them down by putting ice cubes and letting heat flow out. This would be referred to as diabatic heating, where you actually have heat flow into and out of the system. Adiabatic heating, I don't touch this knob at all down here. So if I want to heat these molecules adiabatically, what I have to do is squeeze them together. Now remember that the temperature is related to the average kinetic energy of the molecules. When this wall moves and whacks into the molecules actually bounce off the wall faster than when they collided. It's kind of like a baseball bat hitting a baseball. Okay, and so this would be adiabatic heating. No heat flows into or out of the system, but the temperature goes up because the wall actually adds energy into the system, the movement of the wall, the compression. And now I can cool this adiabatically by expanding it. And notice when the molecules hit the expanding wall, the wall that's moving away, they bounce off slower and the whole thing cools. This is how clouds form. As the air rises up into the atmosphere, the air pressure becomes lower and lower, and the air parcel expands and cools and eventually gets to the dew point temperature. Okay, good.